Hey everyone, this is Pwn checksumz as part of IrisCTF a couple of weeks ago, and this challenge was written by Lambda. I got first blood on the other two Pwn challenges, but I didn't get first blood on this one. I was actually pretty late on this one. But it was a kernel challenge. It was pretty fun. We're going to be exploiting a arbitrary out-of-bounds read, out-of-bounds write, and then we're going to use that to get a KSLR leak, and then from there we're going to overwrite a mod probe path. So for this challenge, we're given a download file. In the download file, this is the exploit file. To start out with, kernel challenges have like a little bit of setup, so if you've never done one, it can seem like a lot. I'm going to recommend this again, but I highly recommend Pwn College. They have a whole module on doing kernel exploitation, and that's where I learned everything, that and reading write-ups, and it's really good, especially for just like building confidence. Once you have confidence, like a little bit of confidence in doing kernel challenges, they actually become fun, and then you learn more and you get better, but I feel like there is like that initial hump to getting started with them. But hopefully I'm going to take this one a little bit slow, and so if you've never done one, maybe this can be a little bit of an introduction, but I'd highly recommend doing Pwn College. So the challenge author, Lambda, they gave us a whole bunch of like startup files. It is much appreciated. Sometimes some challenge authors are not quite as friendly, but this is amazing. They show us how to do the debugging. They give us nice make files. They make it very easy to get started. So we have the start.sh. Pretty much you just run this and the challenge starts. I'll do that real quick. Start.sh. And bam, we are in the QEMU instance, which I'll talk about in a second. And this is the challenge. And so it gives us information. The target care dev can be found in dev checksum. So, I mean, this is just a file. We're going to talk about how you interact with it in a second. And to get the flag, you need to read dev VDA. And so we can see we can't do that. We're currently user 1000. Cool. So as I mentioned for a second, it is using QEMU. I believe this stands for quick emulator, but people just call it QEMU system. And so what's happening is there is a kernel image, which we'll talk about in a second, and it is just being virtualized onto this QEMU system. So QEMU is pretending that it has all the hardware and it's running the instructions. And so the kernel has no idea that it's actually running on this virtualized environment. It's just running as it normally does. But QEMU provides just a beautiful interface to interact with it. And since it's virtualized, if it crashes, it doesn't crash our system. So we could run, a whole bunch of different kernels at the same time. We can do whatever we want, thanks to the magic of QEMU. So we have the kernel. Again, it's just a giant executable. It's actually an L format. We have the initramfs. So this is our starting file system. This will be all the the /etc folder, the /op folder, the /home folder, all that stuff. Everything, within your root folder is loaded as part of initramfs. And so if you wanted to put more files into that QEMU instance, you could, it's not unzip, they use a CPIO, some sort of compression mechanism, and you can add more files and then recompress it. There's some other stuff that's not too exciting. This is a lot of the same standard stuff. There's these protections here. There wasn't a big deal for this challenge, but sometimes protections will be here. There's smap and smep. I'm going to skip this. If you do more kernel challenges, eventually get there, but the video is also already pretty long. And this is where the flag file is loaded. And so they said you have to read the file from dev VDA. This is how it gets loaded in. And so when we use the start script, we can also run it with the debug mode. And what this will do is QEMU system has some bindings for enabling GDB. So you can directly attach GDB to the kernel and debug it like it's any other application. And it works very well. It's completely seamless and very cool. So those files I was mentioning that there's like an executable and all that stuff. That's in here in the artifacts folder. There is the VM Linux. So this is just the raw kernel image, just an ELF file. We could load it in Ghidra and decompile it if we wanted to. We're not going to do it. It's a big file, but you could. This is that initramfs. This is just your file system, just compressed. This is the kernel module we're going to talk about in a little bit. And so this is the actual target of the challenge. And then this is the compressed kernel image, just this, but with some compression. And I think it's like put in a specific format for being loaded as a kernel and all that stuff. Cool. So for these kernel challenges, we attack things called kernel modules. Like, it doesn't have to be this way, but most of the time when you're doing a kernel CTF challenge, it's going to be a character device kernel file, and you're going to have to exploit it. So the way these work is, actually, I'm going to go over to terminal. I'm going to actually go, so this is like my host machine. I'm going to type lsmod, and what this is going to do is it's going to list all the kernel modules that are loaded into my system. And so this is code that is in the kernel that was loaded at some point that provides the kernel with extra functionalities. A good example is, I don't have it plugged in right now, but I have my PlayStation controller, for example. If I want to use my PlayStation controller, at some point it loads in a kernel module. I can't do it right now because it messes up the sound with the microphone, but you'll see like it's like PlayStation HID or something like that. And so there's a kernel module that handles all the drivers for the PlayStation. Like most of the time, most people aren't gaming or using a PlayStation controller on Linux. And so because of that, like not everyone should have the PlayStation drivers loaded into the kernel. But once there is a PlayStation controller connected, it'll load it and we have that extra functionality in the kernel. And so most of the stuff is like dealing with device drivers and stuff like that. But there's a whole bunch of stuff for like sound and who knows what else. So when we go into the challenge, and we run lsmod, the only device driver here is the vuln one. And so this is the one we're going to be exploiting. As part of this kernel driver, it registers a file at dev checksumz. So this is how we interact with it. Like it's not like a real file. Like there's the Linux philosophy of everything as a file. This is just how you can interact with it. And when we call certain syscalls like open and read and write, there are handlers defined for this file, which we'll see in a second, and that's how you interact with it. There's also a syscall called ioctl, which is another way, and we'll actually see it in this challenge for interacting with these types of files. And we can see it's a C, it's this a character device. Cool. So how does one set up one of these or build one of these kernel modules and do its stuff? Oh, also, if you want to load the kernel module, there's mod probe, or you can do insmod, I think, and you can just load the kernel module. And that's how, if I think you have to be root to do that. I mean, you do have to be root to do it. And then it'll load the kernel module, give it a random address and blah, 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 and set everything up. Cool. So when registering a kernel module, so this is the challenge file. This is that vuln.ko object we saw earlier. And this is all the code for it. So we're going to be like poking through this file, finding the bugs and exploiting it. But looking at how kernel modules kind of work, for CTFs, this is like this is like the router of the web app. Like this is what usually you're going to look at first to kind of see what functionality you have access to. This is your attack surface. So there was that dev checksum file. When you call open on it, like the standard open syscall, like opening another syscall, it is going to call this function, checksumz open. And so we can scroll up a little bit. This is the checksumz open handler, I guess. And so when you call open, this code will execute. I'll just go over it real quickly. It's going to do a little kernel alloc. So it's kind of like the heap. It's called slab though. We'll talk about it a little bit later. It's going to create this structure called checksum buffer. So we just have this big checksum buffer object. We can go to the definition real quick. It's just a pointer, a state, a size, read, name, S1, S2. I guess I should also explain this checksum buffer, what it does, or sorry, this checksum driver. What's happening is you can write to it, and then you can request that it gives you the checksum. So really, this shouldn't be in kernel space. It's kind of silly, but it is, and it makes for a fun challenge. And so as part of that, there's a buffer. When you fill up the buffer, you can take the checksum of it. So we have a pointer into the buffer. The size of the buffer is 512 bytes, and it's a static 512 bytes. Let's go to definition. We can see it's just right here, char state 512 bytes. There's the read pointer. It is given a name, which is also another kind of like malloc, but a kernel version. Again, we'll talk more about this later. And then 2 internal state variables for when calculating the checksum. We then copy the name default into this name field, and then we memset the buffer to 0. And that is what open does. And so we can go through all of these. There's also release. So when you close the file, there's ioctl. Ioctl is, again, very common in CTF challenges and just device drivers in general, but very useful for CTF challenges. It's a way to kind of like not every operation a device has can be mapped to a existing syscall. So obviously we have like open, read, and write and stuff, but like maybe you want to do something that doesn't really align with a syscall, and so you can use ioctl for that. And what happens with ioctl is you can pass, you're going to call it on the file descriptor, so you open the file, and then with that file descriptor, you're going to pass it a command integer and then an argument integer. I mean, you don't have to use the argument. And so then on the kernel side, it can take whatever that command is. So like say this command, checksumz ioctl rename, this is just, an integer. It'll then do the rename command. So this is how you can kind of do arbitrary stuff without using the full syscall or like a dedicated syscall. Then there's a function to write to the buffer, a function to read to the buffer, and a function to seek into the buffer. And if you're not familiar with seeking, it's just kind of moving the pointer around in a file. So there's a couple little bugs in this challenge. One of them is in this write iterator. So the way this works is, so again, you could just call write. So you're going to do write on the file descriptor. You're going to give it the buffer that you want to write and the size that you want to write. So again, in our C exploit that we're going to write in a second, we're just going to write code like this, and it's going to call this function. So we have the file description. So this is doing the write iter. It's just like a newer way to call write. We don't have to worry about it too much. Basically, we're just going to do write. There's also like an asynchronous write version. There's a whole bunch of different handlers for all this stuff. So taking a step back, that file operation structure we were looking at, so we defined lseek and like open and a couple of them, but these are all the different handlers we could register on that file. And so you can register just vanilla read and write, but there's these updated structures, read iter and write iter, and but we could have, I guess the challenge author could have used these, but I think these are the recommended interfaces to use. So anyways, so we're going to write, to this file descriptor, some contents and some size. And what it's going to do is first it's going to retrieve that original buffer it allocated. And so you can save a pointer on this field called private data. Again, this is not too important, but you're just able to save data and you can use that as storage, and this is how it works. Then we're going to count the number of bytes in this iterator. For us, again, we're using the write interface, so it's just 16. So this is just how you extract it from this like weird iter interface. So we're writing 16 bytes. It's going to just do some quick checks to make sure that the buffer exists, the count exists. And then when the kernel wants to copy data from the user, it's supposed to use this copy from user function. This one's copy from iter. It's very similar, but this is how you copy just data from user land to kernel land. And this, there's copy from user, copy to user. They provide certain security guarantees. I think I mentioned that there was this thing called smep and smap. You have to use these functions, otherwise, because these protections are on, you can't just access user land memory, and this is for various security reasons. Pretty much any system you look at now is going to have smap and smep enabled, but basically it used to be that you could trick the kernel into executing user land code, like jumping back to user land code, even though it's still in the kernel execution context, and so you can be executing as rank 0, or sometimes you can do some tricky stuff with just getting it to use user land buffers incorrectly. So anyways, now the kernel is not allowed to interact with userland code or userland memory directly. They have to use one of these copy to or copy from functions. But anyways, we're going to copy the data from the user. So this is the kernel buffer. We're going to copy at state plus the current position. So this should be between 0 and 512. And we're going to copy either 16 bytes or the size of bytes, whichever is smaller. So a maximum of 16 bytes. And then from is the user buffer. Cool. So you might have noticed a bug here. So what happens if buff.position is 511? It's not greater than the size. There's no side checks here, but we would overwrite the bounds of buffer.state because, buffer state, because it is only 512 bytes. So we already can write, 16 or 15 bytes. I don't know if there's an off by one, but at least 15 bytes past the bounds of buffer state. So that's interesting. Then it's going to update, the buffer position, see if it's plus equals the number of bytes copied. It's going to see if it's greater than the size, and if it's greater than the size, it's going to set it to 511, I guess. Cool. So we have a overwrite. So we can see what exists in memory afterwards. Thankfully, the buffer was aligned so that it's the same as the structure definition. So it is aligned like this, and you can expect that in GDB, which we can do in a little bit. So we have the position pointer that points to a position within the state buffer, and then right after the state buffer is the size buffer. So we could modify either one of these. Our target for modification is going to be to this one. So again, we're going to set the position to equal to 511. When we do that, we're going to fill in a garbage byte, and then the next 8 bytes we send are going to overwrite the size field. Cool. When we do that and we go to the read function, so there was the write function, this is the read function. It's going to do a lot of the same stuff. It's going to do some basic checks, and then it's going to copy from the user buffer into a userland buffer, and we can copy up to 256 bytes. Cool. So we have a arbitrary read past the buffer, and we can write 16 bytes past the buffer. And it gets even better. It's going to do some bounds checks here to see how far the position buffer can be, and that's dependent on buffer size. And since we can overwrite buffer size to OXFFFFFF, we have an arbitrary relative read pretty much anywhere past buffer state, because we're just going to set the size to the largest possible. So we can, wherever buffer state is, it's going to be in the slab, but wherever that is, we're just going to keep reading as much as we want. And since buffer.size is also large, once we do that overwrite, we can do that relative write anywhere past the bounds of buffer. So we have lots of things to look at and play with. Then the last bug is this IO rename. So this is part of the ioctl syscall. So this is just how you can kind of call arbitrary code on the character device. So we're going to pass in the command equal to whatever this value is. And what it's going to do is it's going to copy from the user into the internal buffer name the data that we pass it for 48 bytes. Buffer.name is a pointer. If we remember, this was actually allocated with the kernel alloc, so kz alloc. So this is a pointer. So if we could overwrite the name field, we could do an arbitrary overwrite of 48 bytes to any address we want. And this name buffer is after the state buffer. It's all the way down here. So what we're going to do is we're just going to fill in arbitrary addresses here. Then we're going to do that renaming feature, and we can just write whatever we want, wherever we want. So the next question is, what do we want to overwrite? And let's actually take a look and start playing with stuff. So to do this, I'm going to just do 2 terminals. We are going to cancel this. We're going to do start.sh, and we're going to run it in debug mode. Cool. And then in this one, we're going to do GDB x attach. They give us a GDB. Cool. They gave us a little GDB profile, so everything just works correctly, which, again, the challenge author was super friendly. So this GDB is attached to the kernel, which is pretty crazy. So we're just debugging the kernel like it's another application. So what I'm going to do is I'm going to set a breakpoint on checksumz open. Cool. And then I'm going to hit continue, and then we're going to trigger that checksumz open just so we can play with it. So I'm just going to cat dev checksumz, and that'll call open on it, and our breakpoint is open, and we can see we have a breakpoint on checksumz open. So this is how you can start, debugging stuff. Cool. From this point forward, I'm just going to do some single step so we can see where we are here. There's some registers up there. I'm going to do single step, single step, single step, single step, single step. This is going to do the alloc. It has a different name for some reason. I'm not too sure why. We're going to do some single steps, blah, blah, blah. Next, next, next. And I'm just going to go to the end of the file. Did it open? Oh, it did end. I think then that this might be the address. Let's check. That is not it. Uh-oh. Let's check this one. E, A, B, C. There we go. I found it. I should have gone slower through the function. Anyways, this was the structure that was allocated. This is our checksum buffer that kind of gets referenced every time we make a syscall. We can see the position by default is 0. The state is 0. The size is 512. And the name is default. Cool. So we found our structure. And so at this point, like if you're going through the challenge, you're going to set breakpoints on all the other functions, and you're going to call and make sure that your exploit can actually interact with these functions correctly, and the structure gets updated as you expect. But we can see everything looks good. Like I said, for this exploit, what we're going to be doing is first we're going to do that overwrite past the bounds of state so that we can set size equal to, OXFFFFF. At that point, we're going to do another one of those out of bound reads, and we're going to change this name buffer into something interesting so that we can overwrite something interesting and do something fun. Our target is going to be a buffer called modprobe path. Modprobe path. This modprobe path string is a readable and writable string, and it currently points to sbin modprobe. This modprobe function, so this is Linux kernel source code, is used in this function called modprobe, and it is just executed like a normal binary, but it is executed as root, and it is the kernel that calls it. There's this user mod helper, or call user mod helper exec. Again, the kernel will call this binary as root. And it calls it when it's executing a file and it doesn't know the binary format of that file. So we know we have elf, and I'm sure there's other binary formats. Maybe the shebang handler is also one of them. But if it has a unknown file format, like it can't read the magic bytes at the start of the file, it's going to call this binary, and maybe this binary knows the type of the file, and then it can use the correct bin format loader. But what we're going to do is we're going to create a fake file on disk that it just has some garbage bytes in it. So the kernel doesn't really know how it's supposed to execute this file. It's not an elf. It's not a compact elf or one of the other bin handlers. It's going to call our binary, and we're going to overwrite this path with some other script. We'll just put a bash script in there that just cats out the flag instead of actually returning what the correct type is. And that script will be run as root. I mean, you can put a backdoor in there. I mean, you can do whatever you want. The kernel is going to call a binary or a script of our choice as root. And at that point, we have root on the box, and it's game over. But yeah, it just makes it so simple. Like for our exploit, we just have to overwrite this modprobe path variable with a string pointing to some script that we eventually want to have executed as root, and then later we create a fake file with some garbage bytes in it. We try to execute that garbage file. The modprobe path binary is executed by the kernel as root for us, and we win. So like I said, in this structure, we have this name field, and we can overwrite, rename the name field. So in this name, we're going to put the address of modprobe path, and then we're going to rename our character device to temp evil, and later we're going to call it. The tricky part of this challenge, or the thing that I found most difficult about this challenge, was KSLR. So the ASLR, the kernel is also randomized. Let me exit out of this. Oh, there's only one. We'll do star.sh root. So similar to process ASLR, there's also kernel ASLR. And so that means all the kernel functions are just randomized. So we can kind of see them. So you can do cat proc checksumz. I'm going to do grep modprobe path since there's so many of them. So we can see modprobe path has a pretty random address. It's only 9 bits of entropy though, so it is possible to just run the exploit a bunch and get lucky. I ended up doing that for my script. I just leak some random pointer that I can find somewhere in some other slab allocation, and I run a bit mask on it, and pretty often you'll just get like a reliable pointer or something like that, and you can just, like I said, bit mask it, and you'll know where the base of the kernel is. The better method to do in the intended solution was heap spraying. I think I'll make a video about it, but it won't be in this video because it's already getting pretty long. Then there's also just sometimes there's like little tricks you can do. Like sometimes dmessage will have a leak. Someone will do like a printf. There's like something special you have to do with the kernel leaks in dmessage because there is like a little protection, but there could be one in dmessage, or like the binary will give you a leak or something like that. Cool, so let's cover the solution. First off, you need a way to get your challenge into QEMU. For this particular challenge, it had network access. You can just host a simple Python -m, HTTP server, and just will get the payload, and then run it. Sometimes on other challenges, there won't be network access. So what you'll do is you'll compile your exploit script with Musl, M-U-S-L, GCC, and it's like a very small version of libc, and you can statically link it, and so you get these tiny binaries, and then you just base64 encode it. It's a little bit annoying, but it's one way to do it. For other systems, it would only work for local development, but you can actually mount a file system within QEMU, kind of similar to that Docker script I showed in all of my videos. Similar to that, but again, that'll only work locally, but it can make developing the exploit much faster. But anyways, to do it locally, I just used wget. I'm going to start at the top. This is how we open the checksum folder or checksum file. We're just going to call open on it. You can ignore that. This code is not too clean. Make sure that it was actually able to open. Step 1, we're going to seek to the end of that 512 byte buffer. So seek is just a way to update that internal pointer. We didn't cover the method, but it works just as you would expect. So we're going to call lseek64 on the open file descriptor. We're going to skip forward 510 bytes. And this is just one of the options you pass. At that point, we're going to write some contents. So to call the write handler, we just pass it the file descriptor. Since we're at byte 510, we're going to send 2 null bytes just to finish out that state buffer. And then we're going to send an oxffffff. So we have max int, so we can write pretty much anywhere we want past that state buffer, internal state buffer, and we're only writing 10 bytes. We make sure that it worked well, otherwise we error out. Then at this point, I grabbed the name address. I guess I don't really need to do this. I think I was just doing this to verify everything was working correctly on remote, but there's the existing name allocation that was malloced or done with kalloc, and so I just grab it out so I can print it out and see what it looks like. Then we seek to the end. At this point, we need a leak. So we can read anywhere past the state buffer, and we can write anywhere past the state buffer. Now we're just looking for a kernel pointer so that we can figure out where the base of the kernel is and calculate where modprobe path is. This is not very scientific code, but all I do is I just start dumping a bunch of values, and I interpret them as pointers, and I see, does it look like a valid kernel-based address? And if it does, I say it's an interesting pointer. There was an object I saw a lot of, device k-type. So I wrote a little special handler for that because that's just an easy win. So if I see this pointer, I just assume it's this type, and then I know how far this device k-type symbol is from the base of the kernel, and so then I can just easily calculate that. Otherwise, I just take a random guess. So pointer and this bit mask, I add the value to modprobe path. And we hope for the best. Like I said, it doesn't work every time, but it does work. Now we have a guess to where modprobe path is. We seek to the name buffer, so that's 512 plus 16. At that point, we're going to overwrite the modprobe path address. So we're overwriting, I think just name, and then I don't know what this OX deadbeef thing was for. But we're going to overwrite name. And then at that point, we're going to get everything set up for the mod probe exploit. So we're going to create a fake file. And we're going to call that temp trigger. And so it's just going to be oxffffff. Cool. And that's going to exist on this file. So this file is, it's executable, but just not executable. And we're going to chmod exit. Then we're going to create the exploit script that we want the kernel to run instead of the mod probe binary. And this is going to touch temp nice just as a debug. Then it's going to copy dev vda into temp flag. And then it's going to chmod the flag and put it in temp x. And right in this, our script is going to be saved as tempx. It's just going to chmod the flag. And then we're going to make that executable. Then we're going to do that ioctl call to rename the buffer. So we're not renaming the buffer, we're renaming mod probe path, and we're going to set mod probe path to tempx. And then at that point, we're just going to execute temp trigger. This should call mod probe path, and if everything worked well, it should cat temp flag. So pretty fun. We can see if it's working. Let me do a couple little things. So we're going to do tmux. I'll make this bigger. We'll do Python and actually cd exploit Python hp server Python 3. It's running on port 8000, and we'll see if cool. So it downloaded. We found the name address. Now it's just kind of scanning for pointers to see if we can find one that's interesting. Again, this is not 100% reliable. Like I said, the intended solution had heap spraying, so you can create kernel objects by various syscalls and stuff like that, and you can try to get known. If you have a known object that has like known fields and known kernel pointers, you'll probably get luckier. This one doesn't seem to be working. I'm going to restart it. Oh, we're running as root anyways. Let me not run as root, otherwise that'll probably muck with things. You'll put, like I said, you'll put known objects kind of nearby, and you just spray a whole bunch of them, and then you'll get a leak that is probably interesting. So we found an interesting pointer. It looks good. We're going to hope for the best. And sadly, it did not work. Let's try again. We probably overwrote something else. Who knows what we overwrote? We'll try it again. We found another interesting pointer. We'll see if this one works. So this is 35v9. And we crashed it, so that one did not work, sadly. Cool, and it worked. Not the most elegant solution, but points are points, so no complaints. Maybe I should go back and do the heap spraying, and maybe I'll make another video, a little part 2. Anyways, thanks to Iris for hosting. Again, I love the CTF, and thanks to Lambda for the fun challenge, and I will see you at the next CTF. Cheers.